That's what we call emergence. But the thing is that we have weak emergence and we have strong emergence. And so what we're talking about here is weak emergence. And so what makes this weak? Why do we call it weak? Well, for one thing, we can simulate the behaviors of a bird, say, or a bird flock, or like fireflies. You can replicate that through some sort of simulation, but you can't necessarily reverse engineer it. So you have this simulation of different, like a bunch of birds forming these flocks and maintaining the flocks, or fireflies synchronizing their fluorescence. But you can't, like, say, we have like we can't like trace it back to like single individuals doing things that move the flock, or we can't like reverse engineer all of the interactions. It's just not possible. We can though create a structure that will sort of simulate the original flocking. So we can make good replicas, but we can't really determine any sort of causality. And so the second point is that we can map between the parts and the whole. So we can say individual voids or individual fireflies are doing X to maintain their position in the flock or the structure. But we can't necessarily say that the actions of any one individual cause anything else. So like your question about the barriers, how did the birds go around? Well, the leading edge of the flock try to avoid colliding into that pillar, and then the rest of them follow along, and that's pretty much all we really know. I mean, we can replicate that pretty well, but beyond that, we don't know why or how they do it. So in a causal sense, we have no idea, but we do know that we can simulate that process. And then we can generate or imitate a configuration like a flock, but we can't predict it. So we can't necessarily predict what a flock will do. We can, like in the general sense, say that the flock will avoid obstacles, or the flock will stay together. I mean, just given the rules, and we know that in general that's true. But we can't predict that at any given time in the simulation that the flock will fall apart, for example. And there are cases where the flock falls apart. Maybe the voids get too far apart from one another. Maybe they, you get them into a corner. You generate some environment where they can't avoid obstacles without colliding, and everything falls apart. But we can't predict when that's going to happen necessarily. So, I mean, I want you to keep that in mind, because when I talk about this stuff, it seems like magic, but it's actually like people have sort of characterized that global behavior as well. But we also know that, aside from that, we also know that there are a lot of collective states. So we know that the flock is a collective state. Like I showed you before, we have swarming and polarized behaviors and milling. But we don't know necessarily how to characterize those global states. And so we know how to characterize each individual agent in the simulation, how to generate a flock, say. You just do these behaviors in parallel across 100 or 200 individuals, and you can get these structures. Well, we don't know necessarily how to characterize the group behaviors, nor how to describe those group behaviors as they transition. So this paper actually might help here. This is a paper by a number of people who were studying animal behavior instead of computer simulations. And in this case, they used multiple parameters that they came up with in their studies. They used the polarization parameter, and they used a rotation parameter, for example, in this example. And they measured it over time. So they had a different number of individuals for each of these measurements. And they measured these two parameters over time. And they were able to actually come up with what they call dynamical states, which I think Jesse presented on this earlier in the summer, where he talked about, how they were looking, or people were looking at robotic simulations and, in collective robotics, and they were looking at or I think it was in Bradenburg vehicles actually, and they were looking at how to characterize behaviors in Bradenburg vehicles, not by looking at the output of the network, but by looking at the behavior and doing a dynamical analysis of the behavior. So this is quite different from like trying to characterize Boids as a collection of individuals. This is looking at the looking at the global state and then characterizing how it moves by using different parameters, and then making like statements about like what's the current state of the flock or the school, and then is it transitioning to a different state. So you would observe this flock or school over time, and you'd look at the different states that it transitioned to. It's a very different way of doing it from the Boids example, but it actually gives you a lot of information about the global state.
Mm-hmm.
And then there's something called swarm algorithms. So in this case, we have swarm algorithms, which are algorithms that use these type of rules, not as a way to simulate a flock or a swarm, but to sort of converge upon computational problems. So you have here, in this case, you have a bunch of ants that have to find food, and they're characterizing this in terms of a decision tree, which is, if they're doing something in the environment, they're either carrying food or not, and then they're making their decision based on their current state. So in this case, the ants, they go to find food and then they bring the food back to their nest. And, they have these behaviors where they're making these decisions at every step in the simulation. If they need to find food, or if they're carrying food, do they move it back to their nest? And, they can make these decisions in parallel across this community of ants. People have done this with bees as well, and they've characterized it dynamically, where each individual bee is making decisions and they're optimizing their behavior. So I think I told you before that in swarm algorithms, they do a lot of, they use these things to find global optima in a solution space. So you'll use these agents as ways to explore the solution space. And so if you have a lot of agents and they do these collective behaviors, you'll use metaphors like food and ants for exploring the solution space and finding maybe local optima and comparing them with other local optima. So there are ways to make this, it's an analogy, it's not really a swarm, but you're able to actually explore your problem space using this technique. And so there are actually two main ways to do this in the literature. The first is ant colony optimization. And so this is about maybe both of these methods are about 25 to 30 years old. But the first is ant colony optimization. So people have worked on this specific problem, which is to find optimal paths across the graph using ant-like agents. So in this case, they're actually exploring a graph. They're using a graph theoretic approach to explore this problem space. So, you send these ants out across the graph. They explore different nodes and different paths. And then each ant, when they travel, they lay down this pheromone. And then other ants will follow the pheromone. So and then you weight the amount of pheromone to the better solutions. So the better the solution, the more pheromone there is, and the more ants converge upon where there's more pheromone, and they find the optimal path over a number of iterations. And so this way they're able to find optimal solutions through a graph. Another method for this is particle swarm optimization. So this is kind of using bees as an analogy. And they start with an initial velocity, and there's communication between the agents. And then they use this evolutionary algorithm, which is a sort of an evaluation mechanism to find an optimal solution. So these, again, you have something like the Boyd simulation, and they, do their thing. You turn it on and interacts, and then you use an evolutionary algorithm to find small differences in the particle swarm and say, if you come up with a better solution, the swarm moves towards that better solution. And you use a fitness function to sort of enforce, moving in that direction. So when each individual, of course, is following their local rules, but they're biased towards certain actions by this fitness function. And then eventually all the agents will converge onto some solution, which we hope is the global optimum. And there's this article here in Natural Computing is a review of the sort of the way, there are actually two articles here, the way people have implemented this. And even though it's over 10 years old, I think if you're interested in that, that should give you a good idea of how people do this. It's actually quite effective sometimes at finding the local optimum for problems.
Yeah.
So actually, that's the algorithms. Now, we can actually turn to actual ant navigation to understand what's going on. So this is a shift now to sort of the sociobiology and the insect biology of what's going on in ants. So when ants actually navigate, they actually use a number of modules in their brains to make navigation happen. And so, like I told you with the swarm algorithms, they use this heuristic. They use optimal paths with pheromones. Ants actually navigate using a number of different brain modules. They use a module that measures internal distance and have a homing mechanism, something called path integration, which is where they can actually sense, what distance they've traveled, what direction they've traveled, and go back to their original position. They can also learn visual scenery. They can, of course, track pheromones. They can do systematic searches like looping movements. So they use this path integration mechanism and combine it with sort of like looping patterns or something called levee flights, where they'll explore their local space a little bit and then move around their global environment to find resources. And also backtracking, which is they'll head in the opposite direction of their homing route in case they get lost. So they do all these things to find their way home. And so that's actually a little bit different than the swarm algorithms, or at least the canonical swarm algorithm. So when we think about these swarms and predicting them or like replicating them, we keep in mind that the swarm algorithms are just like a rough approximation of what the ants are actually doing. Now, there may be opportunities to use some of these mechanisms in algorithms, that might actually outperform swarm optimization algorithms. So I had a colleague who actually did her dissertation on path integration and visual and spatial cognition in robots. And so there was, in her case, that was more of a biologically inspired approach. And so there are other ways that people are doing this that are more sort of conform more to what ants do in nature. So, swarm algorithms aren't the only game in town. And then if we think more about like the social physiology of insects, we can understand swarms a little bit better. So we know that there are like these these superficial interactions sometimes between individuals. We know something, but we also know a lot about the social physiology of insect swarms. And so, this argues that there's a role for innateness in the individual agents. So when we model collective phenomena, we give the agents rules, like, very simple rules. Don't collide with your neighbor. Don't, get too far away from your neighbor, and maybe follow your neighbor. But we can also create innate features of these agents too. And this is actually, there's a parallel here with what we've been doing with Bradenberg vehicles, in that we're actually creating innateness in our agents with these nervous systems. And so in insects, we know that there are a couple of innate mechanisms. One being the division of labor between individuals in the colony. So there's some individuals that are queens and some that are drones. And so that's actually in insects affected by a set of genes that actually, control that sort of division of labor throughout life history. So when they're, drones, they have a certain physiology. When they go to another stage of labor, they have another physiology. Unlike humans, they don't learn their behaviors, their work role. They actually, it's hardwired in the individual. And then we can also look at their group level coordination of action, which is actually also regulated internally to the agent. So if we think about like insect swarms, we have to think about these things as well. And then I found a paper actually that talks about a collective intelligence factor. So we've talked about parameters of the group, of the swarm, but in humans they've actually found evidence that there's this sort of collective intelligence parameter that you can measure, which is actually related to the intelligence quotient. And this measures how well groups perform on a diverse set of problem-solving tasks. So this is actually not correlated directly with G. In fact, it's somewhat complementary, but actually different than G, which is the individual intelligence quotient. This is like collective intelligence. So this is actually correlated with the social sensitivity of group members. So what kind of social cues do group members take? And then also sort of their ability to work in groups rather than work on their own. And so this just shows you that there are ways to measure the sort of collective intelligence and that it's distinct from what the individuals are doing. And it has a lot to do with what the properties of the individuals themselves, if they're more able to work in groups or not. So again, this is something that we can look at in terms of the innateness of the individual, or something we can teach the individual agents. And so that's the slide deck I wanted to show you. It was a very, like I said, this is a very just a rough and ready presentation on this stuff. There's a huge literature on this stuff, so it's hard to kind of get into it without really kind of going for 2 hours on it. You have these big discussions on it, but I just give you a quick idea. And like I said, because I had a problem here with the recording, I'll record this. I'll do the presentation separately and put it on the web.
I see. Fine.
So did either of you have any questions about that, or?
Actually, very recently I've been very much interested into this sum and collective intelligence things. So I was looking at many labs, and one of the labs I showed you the link, and they are working on exactly the same things, and like they are actually simulating the thing, making hardware like hardware modules of those things. So it would be very interesting. And thinking about like using the swarm idea in the simulation that I'm doing is like I can add one feature that the like one vehicle is trying to avoid the other vehicles, like trying to maintain a distance. So that might add some new set of like emergent behavior in that. So
Yeah.
yeah.
I mean, it's like we talk about like, designing for emergent behaviors, and then we talk about like designing agents that have things in them, like, different behaviors, and then they engage in this emergent behavior. So like, it may be that like they have to have some degree of sociality, I guess is what I'm saying. They can't just be like these agents. I mean, they might behave in that way. And it's interesting to make the distinction between like agents that just kind of behave collectively because they're in the same place versus like real true like collective behavior. So like in robotics, they do a lot of teams, like robot teams, where they try to rescue people in emergency situations, or they try to do something like a manufacturing task. And in those cases, you have to have really good coordination between the agents. And so in a lot of those cases, they'll do specialized. They'll add in the Boyd's example, you had 3 rules. Well, you might have like 10 or 15 rules in a system like that. But again, those rules, you have to be careful because when you use the rule-based approach, they tend to be like harder to control. So it's a pretty big challenge, I think.
Okay. Yeah. So another thing was like, given we have like lots of vehicles or say agents for that matter, and one of the important properties of Swarm is there's no particular leader. It's like the vehicles or agents are interrelated to each other, like they influence each other, they influence their neighbors. So same thing is happening in our case also, but like we have additionally set up some rules which are also affecting the emergent behavior. So now adding some kind of interaction between them, interaction properties between them. I don't know how that will influence the Betenberg vehicle emergent properties. So if I should go for that or not.
Yeah. Well, the
Mm-hmm.
emergent properties are often like a byproduct of the interactions.
Mm-hmm.
So, I mean, but actually, and I didn't show this in the slides, uh, sometimes like this is what they call bottom up organization. So, like, if you use rules, it's bottom up, right? It's just like
Mm-hmm.
individuals interacting. You can also use top down, and this is usually what we think of as just like controlling a group of robots. Like you tell them to be in this place at this time. The problem why people don't use bottom or top down control very much is because it's impossible to really control. If you
Yeah.
specify everything, then you can't really do any. When things are not like the conditions aren't perfect, you can't control it. The system breaks, and so that's why people have used bottom up approaches. And so, balancing the two actually might be a more effective way, even still, of getting this sort of behavior that you desire, this sort of emergent behavior.
Yeah. There was something called, just like the case you said, there were 3 rules for boys, and based upon that, some kind of emergent behavior just came out of that. So I was reading about something, says Conway's Game of Life. It has some 3 rules, and again some kind of behavior is getting out of that. So while we are writing a paper or something like that, we can like portray the case of Brettenberg vehicle as some sophisticated set of rules which are actually leading to some kind of emergent behavior in our case. So
Yeah,
just to say,
yeah. I think the Conway's Game of Life. That's a pretty interesting. Yeah, that's a very good example. That's with a well, for Ziyi's benefit, in case he doesn't know what it is, it's a cellular automata. So it's this very abstract set of like it's a tile where you have a bunch of squares that where they have local rules. Each cell follows its neighbors, and then you have neighborhoods, and then
yeah,
the neighborhood, over like the entire grid, you have this over the entire tile. You have these complex patterns that emerge, like gliders and things like that. That there's a whole taxonomy of objects that emerge from this, and it's just like turning cells on and off random, and then those cells also following what their neighbors are doing. So you get like maybe if your neighbor turns black, you turn black as well. If your neighborhood is turning gray, you might turn gray. It's like it's not a deterministic system. You're just following the rules and updating them, and then eventually you end up in converging upon some solution that
yeah.
involves like some sort of broader collective behavior. So, um,
Mhm.
so I mean, so I think that was a pretty good talk, even though we had problems with the connection. Uh, I wanted to talk a little bit about the paper too, but I don't think we're going to have time. We're already at the top of the hour.
Yeah.
But thank you, Z, for your comments and your additions to the paper. I went through them yesterday, and they look good. I'm going to be. I didn't get a chance to work on it much this week, just to look through what people have been adding in. So thank you, Z, for your comments, and you made some changes. And I'll probably be working more on it this week. But
Yeah.
okay, yeah, no problem.